KATRIN! We know from the last video TAPIR, tritium IR absorption spectra of liquid hydrogen isotope homologues. And what does KATRIN stand for? Karlsruhe Tritium Neutrino Experiment. The goal was to determine the mass of the electron antineutrino. But what do neutrinos have to do with tritium? Tritium is a beta-minus emitter. The beta-minus decay has been known for quite some time, but there was a problem. When you plot the intensity of the radiation against the energy of the respective beta-minus particles, you get a better spectrum. Okay, so what? What's so bad about that? Until 1930, beta-minus decay, as I have written it here in the equation for the tritium to helium-3, seemed to violate both conservation of energy and the conservation of angular momentum. The measured electron, i.e. beta-minus particle, has a spin of 1/2. However, delta J, i.e. the spin difference between the parent and the daughter nuclides, is an integer. In this case, it ranges from +1/2 to +1/2. 0, which is also an integer. An electron, which always have a half integer spin, initially violates the spin conservation. Something is missing. The solution to the problem was postulated in 1930 by Wolfgang Pauli, with the existence of the neutrino. It must be a very light particle that travels at nearly the speed of light. Neutrinos were then detected in 1956 by Reiners and Cohen as part of the Savannah River experiment. Mass approximately 0. So, how exactly? And we always ask our students the fundamental question about the mass of the neutrino before going into the lab. The question goes something like, first describe the curve of the beta spectrum. Then we get answers like, yes, it is not discrete, as with the gamma spectrum, it has a shape of a Gaussian normal distribution, and with a continuous part on the right side. And the really good ones know the term Poisson distribution, and then comes the question, okay, it approaches the x-axis, but does it also intersect it? And if you zoom in very close to this end of the curve, then you do what KATRIN does. If the neutrino has a rest mass above 0, there must be an abrupt end that is equivalent to the rest mass of the neutrino without any significant further momentum. You need incredibly high amounts of tritium for such measurements, because in practical terms you can only measure the electrons from the beta decay well. Measuring neutrinos directly, good luck with that. And you need high amounts to have a significant counting statistic at all. The effort involved is so much greater than it seems at first glance, because you also have to take into account any possible side effects. That was the rationale behind the experiment, and considering the effort, I think it was necessary to put all of this into context, otherwise it would simply seem very unproportional. For such an accurate measurement of the beta spectrum, you A, need many beta decays, and B, a very low magnetic flux density, since the resolution of the spectrometer for the electron energy is proportional to the flux density. To achieve such a low flux density, the field lines need to have the largest possible cross-sectional area. A few lines spread over a large area will result in an equally low flux density. A massive tank is needed for the large cross-sectional area. This is the heart of the KATRIN experiment. Where can you find lots of low energy beta decays? At an institute with a handling permit for 40 grams of tritium, the TLK. Tritium Laboratory Karlsruhe, which, as of the day this video was shot, circulated a mere 34 kilograms of tritium as part of KATRIN. Roughly speaking, that amounts to around 8 to 9 kilograms per year, depending on downtime. The only problem is a 200-ton, 24-meter long vacuum tank with a diameter of 10 meters could be manufactured in Deggendorf. Oh well, that works. No international shipping object, right? It's just a shame that this river does not flow through Karlsruhe, and the distance between the end of the river and Karlsruhe simply could not be covered by land transport. And what do? You load this big tank onto the Typhoon, which sails along the Danube, into the Black Sea, then through the Mediterranean, then the Atlantic, and the English Channel, before chugging upstream through the Rhine, and then you only need to drive about 7 kilometers overland through Leopoldshafen on a flatbed truck. Awesome! Now advanced tinkering and I can take a look at it. Let's start at the source, which is back there. Every day around 40 grams of tritium is pumped through this source, but needed is much less as it's being circulated. The tritium is also present here in molecular form and has a cozy 25 Kelvin, i.e. cryogenic temperatures. I don't have any video material of that, not because I forgot to record it, but because the magnetic field strength there is around 2 Tesla, which would destroy my cell phone. With a specific activity of 300 gigabecquerels per gram, you have a lot of electrons, almost 10 to the power of 11 decays per second in the system. Even if you don't wait until all of the fed in tritium decays, but extract it again almost immediately, with these quantities you still have enough beta particles. The beta particles are transported by the magnetic field with 2 Tesla. They then whiz around, whereas the tritium is extracted in the transport area, shown here in the differential pump section. Minimum traces of tritium that remain are absorbed by argon frost in the cryogenic part of the pump section. Now we need to change buildings. And now we are standing at the pre-spectrometer. It occupies under negative voltage of approximately 20 kV. Accordingly, it is behind a fence to protect us. Now the electrons, which are originally transported adiabatically along 2 Tesla strong magnetic fields, are transported to the thick main spectrometer, the heart of KATRIN. However, not all of the electrons are needed. As we were told here, only the last 40 electron volts are needed. So practically all of the beta particles are discarded again, but these huge quantities of tritium gas are needed in order to obtain reasonable counting statistics for the few electrons that have between 18.547 and 18.587 kiloelectron volts. Now in the main spectrometer, the electrons fly alongside the magnetic field lines under high vacuum conditions of less than 10 to the power of minus 10 millibars through this metal zeppelin. The high vacuum is necessary to prevent the electrons from losing energy through collisions. But keeping such a device under a ultra high vacuum is an art on itself. I think the graphic shows very clearly what is happening inside. The beta electrons, guided by the lines originally at 2 Tesla, fly along the lines, and by inflating the field lines, you can get down to about 0.2 millitesla. To achieve this and have intact field lines along which the electrons can fly, you need such a large zeppelin. If you don't do that and still reduce to 0.2 millitesla, the electrons would simply slam into the wall. You have to reduce the magnetic field strength because the energy resolution of the spectrometer depends on the flux density, which in turn depends on the field strength. The lower the field strength, the better the energy resolution for the electrons. And we want to determine the endpoint energy of the beta electrons as accurately as possible. At the same time, the electrons are aligned parallel to the field lines with their spin. These tens of thousands of aligned electrons fly against an electrostatic filter with a potential of 18.572 kV. Most of the electrons have now been sorted out, and all those that can still manage it are used for the measurement. The inside of the main spectrometers is lined with parts that look something like this, and I will leave it now to the professional to explain it.
And inside, you in addition have these wire electrodes. Don't know whether you can see them. Very thin wires. And they're tuned to be exactly on the right tension in order to get proper electric properties that we want them to have. And the entire inside of the spectrometer is lined with them.
So it's basically what you see on all these pictures.
Yes,
here.
You see the metal tank glowing, and then these inner structures, these go alongside. Those are all the frames that you can see. They're for the electric field.
For the electric field, okay.
So we need to shape both very precisely, the magnetic field and the electric field, in order to get proper energy resolution for our spectrometer.
One floor up, you come to the silicon detector, which measures these laboriously aligned and filtered electrons. The silicon crystal itself is in this magnetic capsule, and the yellow label are the readout cards for the measuring instruments, which is a little further back. And now again in fast forward. Tritium is briefly fed in. Electrons and tritium fly along here. Tritium is captured by pumped and cryogenic argon, and only the beta electrons remain. These are guided along the field lines into the pre-spectrometer, which has a 20 keV negative potential. The electrons are aligned and reflected in the main spectrometer, where the field density decreases to increase the energy resolution, because the detector measures a spectrum to determine the mass of the anti-electron neutrino more accurately than it has ever been done so far. This video was created in the laboratories for the KATRIN experiment at the Karlsruhe Institute of Technology. Many thanks goes to Alex for the very detailed tour and a warm welcome, as well as to the working group leader Dr. Wendel for the support of this video. And of course, many thanks for Advanced Tinkering for taking me along, and of course to my Patreons for the financial support. With that being said, thank you for your attention and goodbye.